Okay. So let me talk about another aspect of DRAM. How can we reduce DRAM latency and improve DRAM energy a little bit at least? This is tiered latency DRAM. This was one of the readings that I put up also. But if you look at the trend of DRAM latency and capacity, the capacity of DRAM has improved significantly over years. This is an exponential curve over the years. And it's improved by 16x from 2000 to 2011. But its latency has not improved significantly. The latency reduction, this is the latency TRC, the row cycling time that I described earlier, reduced by 20%. And I'm actually really surprised by this 20%. When my students drew this graph, I thought, is there a mistake here? I thought it would be around 10% or so. But it's actually 20%, which is surprisingly high to me. But basically, we had this trend, and DRAM latency continues to be a critical bottleneck, especially if you have latency-sensitive applications. And this has been a hard problem for a long time. So let's take a look at what causes this long latency and why it has been there. I've shown you this DRAM chip before. I'm going to abstract in a different way. This is the cell array we have, and this is the I/O circuitry, and this is the channel. And cell array consists of a bunch of banks, as you've seen. And these banks actually consist of subarrays, because you do not want long bit lines in the banks. These banks are divided into subarrays that have shorter bit lines. And if you look at the subarray, it's a two-dimensional array of cells, and a cell is what you've seen before. And you have the row decoder controlling the word line, and you have the sense amplifiers that the cells are connected to. And each subarray actually has its own set of sense amplifiers. I'm breaking the abstraction that I gave you earlier, and I'm going to break it even more as we go further. So each subarray itself has this row buffer, sense amplifier, because these bit lines cannot be very, very long. That's why the subarray length is actually about 1,000 to 512 cells. So so you have the row decoder. If you want to access a cache block, if you want to access a column, basically it's mapped over here within the subarray, a part of this row. What happens is you supply the row address, the row gets activated, and after that, that's the subarray access latency. And after that, you have to supply the column address, and the DRAM controller, DRAM chip muxes out the data and sends it back. And I'll call this the I/O latency. And the DRAM latency at a coarse grain can be abstracted as subarray latency plus the I/O latency. It turns out the subarray latency is dominant. You can actually have techniques that reduce the I/O latency. So we're going to focus on the subarray latency. So subarray latency, why is the subarray latency so slow? If you look at the subarray, it has a sense amplifier. And the sense amplifier needs to be large. First of all, it has much, it's an SRAM cell. It's much bigger than a DRAM cell. The second is DRAM is actually optimized for capacitor. It's really a DRAM process. And it doesn't like the logic inside there. That's why it becomes large. And the third is you have additional circuitry to amplify. So it turns out the size of this is approximately 100x the size of the cell itself. As a result, what DRAM manufacturers have done is to have a long bit line, basically string together a bunch of these cells to amortize the cost of the sense amplifier so that you get small area. But the downside of this is if you have a long bit line where lots of things are connected to it, you have large bit line capacitance. As a result, you get high latency and high power when you access this. So this is a deliberate choice that DRAM manufacturers actually have made. They designed long bit line DRAM chips. The subarrays have long bit lines. But you don't have to make this choice, actually. There's a trade-off. This is a deliberate trade-off that's been made. You can actually have a short bit line DRAM. If you want to have the same capacity, this is a short bit line DRAM. That's what it will look like. This is much faster, right? Because the subarrays are shorter, slower. The bit lines are shorter. Of course, this is much bigger also. If you look at this, this is actually kind of to scale. Not exactly, because this is not 100x the cell size. But this is actually much larger area too. So we have a trade-off between area and latency. And let's take a look at that trade-off, how that has played out over time. This is the latency in terms of row cycling time, and this normalized DRAM area of reasonably, of real DRAM chips. This is cheaper. You would like to minimize the area, and you would like to make it faster also. Commodity DRAM has approximately 512 cells per bit line. It could be 1,000. So we're here. We get more than 50 nanosecond latency with this area. You can have fancy DRAM today, and this is what happens as you reduce the number of cells per bit line. You can have fancy DRAM today. This is called reduced latency DRAM or fast cycle DRAM. some very low latency see routers use this DRAM at the cost of money, of course, right? So you get much faster latency, approximately 25 nanoseconds, but also much higher area. And I did not plot the pricing over here, but the pricing is actually much worse over here. You don't want to buy this DRAM for your own laptop, unless you really care about the latency. So our goal is to achieve something over here, basically. And we're going to try to do that. We're going to approximate the best of both worlds. So how do you approximate the best of both worlds? Remember, long bit line has small area but high latency. Short bit line has low latency but large area. We're going to try to get the green without the red. Or we're going to try to avoid the red somehow. If you want to get only the green but not the red, that's magic, I think. It's very difficult to design that kind of memory. So our proposal is to start with this long bit line DRAM, such that it buys a small area, but have a low latency area in this DRAM. Basically, have part of it at low latency, and isolate that from the long bit line. So the idea is to add this isolation transistor that divide DRAM to two areas, fast, slow. And that way, hopefully you get small area because you have long bit lines, but you also can get low latency by accessing this portion. This portion is low latency, it's called the near segment. This portion is high latency, it's called the far segment. And that's the idea. You basically have a tiered latency architecture in DRAM. The idea is to divide a bit line into two segments with an isolation transistor. And this is the near segment, this is the far segment, and we're going to characterize that. If you want to access, and the hope is that you keep data in this near segment most of the time, such that you don't need to access the far segment as much. And that's this. I think that will be the innovation going forward. How do you actually do that? So if you turn off the isolation transistor, if you want to access this near segment, you turn off the isolation transistor. As a result, this far segment doesn't really appear to the sense amplifier. So you get reduced bit line length that appears to the sense amplifier. You get reduced bit line capacitance. As a result, you get low latency and low power, and I show you results related to this. If you want to access the far segment, because some of your data will be located there, you turn on the isolation transistor, and the memory controller does this. This gets long bit line length. It has large bit line capacitance. And it has the resistance of this isolation transistor also. So actually you get degraded latency because of that additional resistance. So you'd like to not have data accesses that go to the far segment in an architecture like this. So this far segment accesses high latency and high power. So let's take a look at, let's quantify the latency, power, and area of these different segments. Commodity DRAM has 512 cells per bit line. We're going to look at a tiered latency DRAM that has a near segment with 32 cells, and there's a far segment with 480 cells. And we have detailed simulations through SPICE with the circuit level DRAM models. And power and area evaluation, this is actually a tough area in DRAM because none of these models are perfectly exposed to us in academia. But basically, we do our best to do the power and area evaluation. But if you look at this, this is what you have today in terms of latency. This is a row cycling time. Commodity DRAM has approximately 52 nanosecond latency. Near segment access gets reduced by 56%. So it's about 23 nanoseconds. Far segment access increases by 23%. That's the trade-off. DRAM power, near segment power reduces by 51%. Far segment power increases by 49%. And what's the area overhead? It turns out the additional area overhead of the isolation transistor to ensure reliable operation is 3%. So I was actually surprised by this number because 3% is actually a large number, right, in the entire DRAM chip. But to be able to enable reliable operation, you need large isolation transistors. Okay, so how does latency actually vary with the near segment length? As you increase the near segment length from 1 cell to 256 cells, this is what happens to the latency of the near segment. And it's basically stays reasonably constant up to 32 cells. So you have an initial latency penalty that you pay. Basically, longer near segment leads to higher near segment latency. And this is the far segment latency. As you increase the size of the near segment, far segment latency actually doesn't reduce that much because you pay the cost of the long bit line. Right? Okay, but it's always higher than the commodity DRAM. So where do we fare in this trade-off? This was what I showed you earlier, right? The DRAM area versus latency curve. Our goal was here, and near segment gets us here, as long as we can utilize it. The far segment puts us here. So we're trying to get the best of both worlds, and partially we can get the best of both worlds, as long as we can avoid this far segment access. Then the question is, how do you actually use this? Yes?
What kind of benchmark have you used for this?
So I'll show you. I'll discuss that. A wide variety of benchmarks. And some benchmarks don't fare that well. Basically, you have to keep the data in the near segment if you want to take advantage of this. So this is actually a substrate that can be leveraged by the hardware or the software. And there could be many potential uses. And I'll discuss one potential use as cache. So you can use the near segment as hardware-managed inclusive cache. You can use the near segment as hardware-managed exclusive cache. Basically, near segment can be inclusive of what's in the far segment, or it could be exclusive. If it's inclusive, you're losing DRAM capacity, right? Because you are replicating things in DRAM. If it's exclusive, you're not losing DRAM capacity, but you're adding complexity. And you can read the paper for this exclusive cache. You can get significant performance benefits that way. You can have the operating system or the system software map pages that are hot into this near segment to optimize for latency. And I believe this is a very interesting approach going forward. We looked at this a little bit, and it does improve performance significantly. One thing that doesn't work is if you take this tiered latency DRAM and replace DRAM with it and don't do any kind of intelligent page mapping or caching. That way you don't get benefit out of this. You have to manage this because it turns out, the random mapping into this particular cache or fast area doesn't get you the pages that are accessed frequently. Okay, so let's take a look at the inclusive cache a little bit. So in this case, we have this tiered latency DRAM. This is a subarray. Basically, what we have is you've divided memory: far segment, near segment, and sense amplifiers. And far segment is our main memory, and near segment is our cache to that main memory. There are two challenges. One is, how do you efficiently migrate a row between the segments? Because whenever you want to cache data from far segment to near segment, you want that to be very efficient, right? And the other way around also, when you want to write back data to main memory. And I'll introduce a mechanism that we will use later, probably in the next lecture now, to actually do fast row migration as well. The second challenge is actually the caching question that's present in all caches. I'm not going to tackle this in detail, but how do you efficiently manage this cache? You can employ many different caching techniques to efficiently manage this cache, and the memory controller can manage that. But I'm going to assume a simple LRU cache, least recently used row is replaced. Okay, let's take a look at how do you efficiently migrate data. So if you want to cache one row into this near segment, from the far segment to the near segment, we'd like to migrate that source row into the destination row. In today's memory systems, how you do this is through the memory controller. Basically, the memory controller reads the source row byte by byte, or 64 bits by 64 bits, and writes to the destination row byte by byte. And we don't want to do that, right? That would get rid of a lot of the benefits, because then you're transferring the entire row over the bus, which is a bottleneck, to the memory controller, and you're transferring it back into this cache, which is back in DRAM. We'd like to do this right in DRAM. And the observation is that source and destination share bit lines, and they also share the sense amplifiers. We could actually take advantage of this. How do you migrate the data that's in the source into the destination? Basically this way. You can use these shared bit lines concurrently. Basically, step one is to activate the source row, which basically brings the data into the sense amplifiers. Now, sense amplifiers are charged with the data that's in these cells. And step two is to activate the destination row. If you activate the destination row now, the sense amplifiers drive their data into the destination cells. As a result, you get the data that was in the source row now into the destination row. And this is a very fast migration of one row to another row in DRAM. Migration is overlapped with the source row access, actually. And you get only additional 4 nanoseconds over the row access latency. And we're going to use this to do fast page migration and fast page initialization in DRAM in a little bit, probably. Okay, how do you efficiently manage the cache? I will not talk about it, but maybe you guys are looking into caching algorithms, and your caching algorithm may be applicable over here also. So a little bit about evaluation. You asked about the workloads. We have a bunch of workloads from the database suite, transaction processing console workloads, streaming workloads, spec workloads, as well as random access workloads. It turns out random access workloads are the worst for this kind of architecture. You can imagine why, right? If you're random access, what do you keep in this near segment, right? That's unfortunate. But I'll show you something else that fares better with random access workloads. So this is system configuration. You can actually read the paper for more details. This is averaged across all workloads for 1-core, 2-core, and 4-core systems. This is the performance improvements that you get. It's on the order of 10%. And it's relatively constant. Can you do better? I believe you can do much better than this, actually, if you're more intelligent about what you keep in this near segment. We were not that intelligent. Any row that's accessed in the far segment is cached, and the replacement policy is least recently used. And people have proven over and over that that is not a good caching policy, right? Because least recently used does not necessarily represent the behavior that you have in caches today. And this is what happens to power consumption. So the power savings are even larger, and they're consistent also across a large number of workloads. So basically, the conclusion is that using the near segment as a cache improves performance and reduces power consumption. So what happens with the cache size? So we have a trade-off, right? We can actually increase the near segment length or reduce the near segment length. And this is what happens to performance improvement as you change the near segment length. And as expected, as you increase the near segment length, you get larger cache capacity, but you also get higher cache access latency. Right? So the trade-off, the best trade-off point, the maximum IPC improvement happens at 32 cells. But again, take this with a grain of salt. If you're designing a memory system, maybe you want to put this somewhere else, and I don't know what it is, depending on the workloads. Okay. There are a bunch of other mechanisms for leveraging TL-DRAM that I didn't cover. You could actually have a hardware-managed exclusive caching mechanism that doesn't lose capacity, and I think this is a good idea. And maybe you can develop some other mechanisms as well. As I said, system software-based mechanisms perhaps are even more interesting. What do you do? Can you design a TL-DRAM with more than 2 tiers? Now that you have 2 tiers, what about 3 tiers, right? You can add another isolation transistor. And it turns out you can reduce the latency of that second tier also compared to commodity DRAM, but you add more overhead. And then you have more management overhead also. Maybe you don't want to complicate the system even more. So I think what's interesting here is there's been a big fall off in terms of the latency. If you look at the last level cache latency and DRAM latency, there's a huge degradation in those latencies in commodity DRAM. What we're trying to do is to make that degradation more graceful, if you will, by adding this area that's the near segment. And if you have more than another tier, that makes it even more graceful. If you have another tier, that makes it even more graceful, the way I see it. So it's a graceful degradation of latency as you get farther away from the CPU. That didn't really exist between the last level cache and DRAM today. Okay, there's detailed circuit evaluation if you're interested in that also. Actually, there are a lot of interesting evaluation issues in DRAM architecture if you change it. How do you do the circuit evaluation? And the memory controller, of course, needs to change as well, right? So you have to somehow manage this cache in the memory controller. Okay, maybe I'll summarize and take some questions. And it looks like we're going to be out of time, so I'll cover the rest in the next lecture and then cover hybrid memory systems. Basically, we looked at the DRAM latency problem. It's a tough problem, in my opinion. Another good area to focus on if you're interested in looking for areas. Our goal was to reduce DRAM latency with low area cost. And the observation was that long bit lines in DRAM are the main cause of that long latency. The key idea here is to divide long bit lines into 2 shorter segments, near segments and the far segment, or fast or slow segments. And the idea leads to tiered latency DRAM. This enables latency heterogeneity in DRAM. And you can leverage this heterogeneity in potentially many ways to improve performance and energy consumption. And we've leveraged it in several ways. One thing I've described was using the fast segment as an inclusive cache to the slow segment. As a result, you get significant performance improvement and power reduction at low area cost. And I think going forward, looking at these low area cost, and one could argue that 3% is not low, but if you want to get that latency reduction, I believe it's relatively low. And if you come up with a better technique, that's also great. But going forward, techniques like this that reduce the area, improve latency, as well as reduce power reduction at the same time with low area cost is very interesting in DRAM. Maybe I'll take some questions. I can go on and on, but I think there's lunch that's going to happen maybe in 15 minutes or so, or 30 minutes. Any questions? Nothing? Yes? Embedded DRAM caches, that's a different beast in the sense that I think you're thinking about embedded DRAM that's on chip, right? So that's a different beast. You could still do embedded DRAM caching on the chip in addition to tiered latency DRAM. That would reduce that latency degradation. That would make the gracefulness of the latency even better. So we didn't evaluate on a system with embedded DRAM caches, but this idea is actually complementary to that. Because you can actually build a large embedded DRAM cache at some cost. This actually gives you a huge cache. If you think about, let's do the calculation. A DRAM chip can have, let's say, 64 subarrays. And you can have 32 rows in each subarray. So 32 times 2 kilobytes is 64 kilobytes times 64 subarrays. So you get a very large cache or very large fast area in DRAM this way with relatively low cost. Embedded DRAM is a complementary approach to actually reducing latency, but that's not DRAM itself. Right? Any other questions?